These are examples for Lesson 12.2, Chords and Arcs. Make sure that you've studied thoroughly the 7 different circle theorems contained in this lesson, as they're really important for you to be able to do these problems and understand them. Example 1. In circle P, angle WPV is congruent to angle XPY, both central angles. Find the length of arc WV here if the length of arc XY is 4.6 here. Since angle WPV is congruent to angle XPY, their corresponding arcs must be congruent. By the congruent arcs theorem, arc XV must equal the length of arc XY. And since they gave us arc XY is equal to 4.6, then the length of arc WV must also equal 4.6. Example 2. In circle Q, arc or chord EH is congruent to chord FG. What is the measure of arc or angle FQG if the measure of angle EQH is 89 degrees? Well, since EH, chord EH, is congruent to chord FG, then by the congruent chords theorem, the measure of angle FQG, central angle, has to be equal to the measure of that other corresponding central angle, angle EQH. And since the measure of angle EQH they gave us is 89 degrees, the measure of angle FQG must also equal 89 degrees. Example 3. In circle T, the length of chord UP is 28 inches. And the length of chord SR is 28 inches. Congruent. What is the length of arc UP if the length of arc SR is 39 inches? Well, since UP, chord UP is congruent to chord RS, then by the corresponding arcs and chords theorem, the length of chord or arc UP must equal the length of arc SR. And since the length of SR is 39 inches, therefore the length of UP, arc UP, must be 39 inches. Example 4. In circle Z, The length of SZ, from point S to Z, is equal to the length between points T and Z. They're equidistant from the center of the circle. This point here to here, and this point here to here. Find the length of chord LK right here. Well, notice that since these are equidistant from both these chords are equidistant to the center, then by the equidistant Chords theorem, LK, or chord LK, must be congruent to chord MN, and thus the length of LK must equal the length of MN. The length of LK, according to our problem, is 4x minus 1, and the length of MN, chord MN is x plus 14. Now we're going to solve for x and then find out the length of chord LK by using this right here. So subtracting x from both sides, we get 3x minus 1 equals 14. Then adding 1 to both sides, 3x is equal to 15. Divide both sides by 3, and x is 5. Using 5, therefore, LK, what we're looking for, the length of it, is equal to 4 times x, which is 5, minus 1, which gives us 20 minus 1, which gives us 19. So the length of chord LK is 19. Example 5. In circle A, chord KE is perpendicular to the chord which is a diameter, HF. We know HF is a diameter because it goes through the center. Arc HE's length, right here, is 3.8. And the length of segment GK, which is part of this chord, is 2.7. What are the lengths of arc HK and segment GE, which is a part of this chord? So since HF is a diameter and is perpendicular to the chord EK, then we can use the diameter bisector theorem. By the diameter bisector theorem, we now know that the length of HK must equal the length of HE. So HK's arc and HE's arc have been cut into congruent pieces by the diameter. And we also know that segment GE must be equal to segment GK. The two segments of the chord has been bisected. So since we know that arc HE is 3.8, arc HK must be 3.8, and since we know that segment GK's length is 2.7, that means GE must also be 2.7. So this is 3.8, this is 2.7. Example 6. Here we have a proof given circle O with diameters AC and BD. They want us to prove that triangle AOB is congruent to triangle DOC. Recall the theorems and postulates we used back when we were proving triangles congruent. SSS, SAS, AAS, those. So if we can use one of those in the course of our proof, that will help us prove that the triangles are congruent. So we take circle O with diameters AC and BD was given to us. Statement number 2, OA, segment OA, segment OB, segment OC, and segment OD are all radii of circle O. We can say that because they all start at the center and they go out to a point on the circle. That's the definition of radii, or radius. Radius of a circle. Once we've established that, now we can say that radius OA is congruent to radius OB, which is congruent to radius OC, and which is congruent to radius OD. So all four of these are congruent by the congruent radii postulate. All radii of one circle are congruent. So now we have, in our triangles, we have two sides congruent here and here. There are a couple of ways to prove this. In this particular theorem proof, though, we're going to use these two angles and use SAS. Angle AOB is congruent to angle DOC by what? The vertical angles congruence theorem. Now we have enough using SAS congruence postulate, to state that triangle AOB is congruent to triangle DOC. And we have proved what we set out to. Example 7. Find the value of the given variable in the circle. Round the value to the nearest tenths place. Well, here we have circle K. Notice we have a radius KJ, and the radius is what they're wanting to know how long is. It has the variable x on it. Then we have a chord LM. Notice that this segment right here, KN, is part of a diameter. As long as it goes through the center, it's always part of a diameter. So since KN is part of the diameter, then we can state by the diameter bisector theorem that LM, where it crosses right here, KN, causes these to be congruent to each other. So this diameter, or this KN, which is part of the diameter, cuts the chord LM into two congruent parts. And so LN is congruent to MN by that theorem, and the length of LN has to be equal to the length of MN, of course. Or another way we could put this, instead of saying this is congruent to this, we could say that the whole thing, since we've got the whole thing in a measurement, LM, half of it, has to equal the part we might be interested in, which is this right here, LN. Now, why do I say we're interested in LN? Because since this radius, since all radius of a circle are the same, this radius, doesn't matter where we put it. If we decide to put it in another location, say right here, this is still x, the length, because it's a radius in the same circle. And all of a sudden we created a right triangle. Always look for right triangles if you can. Well, now that we know this is a right triangle, maybe we can use Pythagorean Theorem or something that we've learned before about right triangles. So anyway, the whole thing is 14. So if I use this and I put in the 14 and take half of it, I get LN right here. So half of 14 is 7. Now that we know this is 7 and we know that this is 3, these are legs of a right triangle, so we can use Pythagorean Theorem. So by the Pythagorean Theorem, we can now state that hypotenuse LK squared equals leg LN squared plus leg kn squared. Substituting in those values, we have x squared equal ln, which is 7 squared, plus kn, which is 3 squared. Then we have x squared equal 49 plus 9. And then we have x squared equals 58. Taking the square root of both sides, we get the square root of 58. Square root of 58 doesn't simplify, but it doesn't matter because they asked us to round to the tenths place. So we're going to approximate that, and when we use our calculator to approximate that, we do get 7.6 centimeters. Now that is the length of LK, which is the same as x, but it's also the length of KJ because all radii in a circle are congruent. KJ, which is x, they're all the same thing.